Hello, welcome to part 4 of my Neos NPC experiments. I have the collision avoidance working well enough that I think I can demonstrate it, even though it is not final yet, most likely. Let me show you what it looks like first. So here is our NPC and the target he's walking to, which he is looking at. But if I put the target on the other side of this wall here, and then tell him to walk to it, he sees that there is a wall in the way, goes around it. Right around the end of the wall, and over to the target. Target achieved. Alright, I will try to describe the kind of theory of operation here first before I show any details of how it was implemented. So what this guy here has is first a straightforward raycast that just looks straight ahead of him, and that says if he gets too close to an obstacle, he stops and doesn't walk through it. And it's actually a little bit more sophisticated than that because I added a thing where he'll start to get slower and slower walking speed as he gets close and then come to a stop before he hits it. Which would be fine if he wanted an NPC that just wouldn't walk through things and would get stuck on every single thing he walks up to. But that's not ideal. So in addition to the forward raycast, I added 2 more raycasts to either side at an angle like this. And that says if he comes up to an obstacle, he looks at the 2 sideways raycasts, left and right, and whichever one is indicating more clear distance, he turns in that direction. So if he's walking up to an obstacle and the raycast on the right here shows that there is more space than the raycast on the left, he turns towards that open space. Whereas if the raycast on the left says there's more open space over there, he turns that way instead. So in combination with the forward-facing raycast, he will walk up to an obstacle, say, oh no, I'm going to hit something, and switch away from pointing at his target to just trying to avoid the obstacle. And then once he's clear of the obstacle, and all 3 raycasts, the forward, the right, and the left, indicate that there is free space, then he will turn back towards the target, wherever that happens to be, and stop the obstacle avoidance stuff. So that's the basic theory of operation. Actually implementing that was a little bit more complicated. It took me a couple tries to get it right. So the first thing we had to do here was, remember on the previous version of this, the NPC would look towards the target always using a look at component. But if we want to turn left and right to avoid obstacles, we can't do that. You can't always be looking at the target if you have to turn left or right. So I added some logic in here to determine, does he turn left or right each frame update. I'll show you that. So yeah, the logic has gotten a lot more complicated. If I look at the rotate, this I believe happens every update. This is just saying if walking, so currently he doesn't turn until he's walking. So on update, if he's walking, it goes to this logic method called calculate rotate direction, which based on whether those raycasts are hitting anything, that will make him turn towards the target or turn away from the wall that he's walking up to. And after this has finished calculating a turn direction, so left, right, or straight, we come back here, and this value field stores the speed of rotation. So he's currently set to rotate up to 75 degrees per second times delta time to accommodate frame time. And then this value field here stores which direction do we want him to go, which was calculated by this calc rotate dir up here. And that'll say I believe it's negative for left, positive for right. And just to make the movements a little smoother, I have it calculating, varying values between -1 and 1. So right now it's a very small value. So we take rotate speed times rotate direction times the vector that we want him to rotate around, which is y for vertical. We want him to look, left and right. We don't want him to flip face down or something. Multiply that to get, a 3-component rotation direction. Convert that to a quaternion, and then we take current rotation times the rotation quaternion, which just means rotate his current rotation by this amount, and then plug that into a set local rotation. And that just says, okay, we turn a little bit left, a little bit right, or just go straight every frame. So it's just left, right, straight, update. And of course things get slightly more complicated in calc rotate direction. Let's look at that next. All right, calc rotate direction is actually moderately simple itself. I don't know why these cards rearrange themselves. So these, I guess I should start at the beginning. So there's the calc rotate direction. Go down here. What this is saying is these 3 cards right here are value fields that store the distance that each of the 3 raycasts detected. So the forward, the right, and the left, they're stored in these 3 value fields. And we look at the closest one. So this is saying look at the closest hit for our 3 raycasts, forward, left, and right. If the closest hit is greater than this value, which I just created something I didn't mean to. So this value says, why is it doing that? This is another value field, which, why can't I pull that out? There we go. 3 meters. This value field says at what point is it clear to turn back to the target. So at 3 meters, we assume that we're clear of all obstacles and we can turn back to the target. So if the closest hit is greater than 3 meters, then we execute the dynamic impulse trigger, turn to target. So that's the code that turns the NPC back to the target. If one of the 3 raycasts was less than 3 meters, then we are too close to an obstacle. We do not want to face the target. It goes down here instead. And if the closest of the 3 raycasts is less than this value, 2 meters, which is the how close to the obstacle you have to be before you start turning away from it, then we execute this dynamic impulse that says turn away from collision. So between 3 meters and 2 meters, these 2 values here, which I'm still having trouble pulling that out for some reason. There we go. If it's between 3 meters and 2 meters, it comes down here and writes 0 to the turn direction, and it just keeps going straight. And that probably doesn't seem intuitive at first, and in fact, in my initial pass, I used the same value for these 2. It was either turn towards target or turn away from obstacle. The problem was that when the NPC would walk up to a wall and start going along the wall, he would jitter a lot because he was either turning towards the target or turning away from the wall. He was just going away from wall towards target, away from wall towards target, away from wall towards target. By adding a little hysteresis here where he turns away from the wall, but the raycast against the wall is in between 2 and 3, he'll just walk straight beside the wall. And that just removes that jitter in that situation by allowing him to walk straight beside a wall. Hopefully that made sense. Like I said, it took a lot of experimentation to get here myself, so it may not make sense. It may not even be the best way of doing it. You may have a much better way, but this is what I have so far, and this is why it's NPC experiments. So inside this calc rotate direction dynamic impulse, there's two others just to simplify the logics, not have it all packed into one thing. One says turn towards target, one says turn away from collision. Let's look at those. So turn towards target, and you may remember our whole goal here is to calculate a left or right angle, and this is the code we run if we want to look at the target. So this is using a value called direction, I believe that's direction to angle the target, which has a value in it that is the rotation around the y-axis that this would have to point to look at the target. I know this is complicated. I don't know how to simplify it more. So if it's a negative angle towards the target, we say it's less than 0. We give it a -1 to indicate we're rotating left. If it's greater than 0, we give it a +1 to indicate we want to rotate right. And this thing down here is just a bit of code that says when we get close to pointing at the target, we don't spin so fast, we slow down our turn rate, and that was just to make things a little smoother, and also so that it wouldn't, look to the left of the target and the right and the left and the right and jitter there. So we take the angle that we need to turn to face the target, which I guess it would be useful to show you. See, right now it's -8 to the target. If I move this, now the target is 47 degrees left. Now it's 38 degrees right. So that is just negative is left of NPC, positive is right of NPC. Now 180 is straight behind. And this is saying this value is 15. So when we're within 15 degrees of the target, we start slowing our rotation down. Okay, so we take degrees off from target, divide by this value, which basically sets the number of degrees within which it starts slowing down, and then we clamp that between 0 and 1, and that gives us a multiplier of which to turn more slowly when you're near the target. So if we look at the output of that, if it's right on the target, it's got a small multiplier. It's not going to turn very much. At like 8 degrees off of the target, it's turning at half speed. At 15 degrees off the target, it's turning at full speed. And anything more than 15, it turns at full speed. Now that may leave you wondering, how did we calculate what the angle to the target is? Which is yet another thing here. So to calculate the angle which is needed to look at a target, so the relative rotation between the NPC and the target, or the NPC's current direction and the direction that it needs to rotate to face the target, we take the position of the target, which is this bottom one, position of the NPC, subtract the NPC's position from the target position, which gives us like a vector pointing from the NPC to the target. And then you use the look rotation node to calculate that angle that would make the NPC look at the target. And this down here is just its up direction, so, facing up. If we spin around up, which way do we have to go to look at that? Then I take that and I transform this rotation, which is currently in global coordinates, into the NPC's own coordinates. So it gives us an angle relative to the NPC and not an angle in global coordinates, which would be not too useful for us. And we take that rotation and take just the Y rotation out of it, because I don't care if it would need to rotate, up or down to look at the target. I only want to know its rotation around the vertical axis. And I just drive that into a value field here for access from other functions easily. So you can see that, that is the angle that the NPC would have to look at and have to rotate by to see the target. And I'm only looking at the Y. I don't care if it would have to rotate around X. All right, what have we not covered? That was rotate to target. The other bit was turn away from collision. So this is the code that calculates the left or right turn direction if you are trying to avoid a collision. Let me see if I can remember what all of this does, even though I just wrote it an hour or two ago. All right, so these two value fields down here are the left and right raycasts, like the distance at which the raycast detected an object. 999 is when they don't hit anything. So we take the two left and right distances and we rotate either left or right and write that into the rotate direction. So this is basically, if you write 1 and -1 into here, that will make it rotate left or right. Okay, this code up here just says when you're still far away from running into something, you rotate more slowly. And the closer you get to it, the faster you rotate, up to a maximum of 1. So +1 or -1 left or right. But if you're a long way away, you start turning slowly instead of just snap turning away from it right away. So that's just taking a couple settings here, which are, the distance at which you start rotating and the distance at which your rotation is full speed. So at 2 meters, you start looking away. At 1 meter, you're looking away as fast as you can, turning away as fast as you can. Remaps that 0 to 1 so that at 2 meters, you wouldn't be turning at all, and at 1 meter, you'd be turning full speed. At 1.5, you would be turning at 0.5 speed. Clamp it, and then write that into the left or right rotate direction. Honestly, I think that's most of it. I mean, I could show you the code for the raycast, but this is the same as the ground-based raycast you saw earlier, so it's nothing too exciting. It's just 3 raycast 1s that on each update, it raycasts along the forward direction instead of down, so 1 forward, 1 to the right, 1 to the left, as defined by these source slots here. That one, and that one, and that one. They all raycast 5 meters. They all have 0 offset from their slot. They all go +Z. And each one, if it hits something, it writes the distance into its associated value field. If it doesn't hit anything, it writes 999 into the associated value field as just a stand-in for no hit, maximum distance away. And that's most of it. I did change the walk logics. So this is the logics that instead of dealing with rotation like we've been talking about, this deals with its position. If you have recently watched an earlier video, it will be quite similar, except that we have a new section down here. So this is all the same stuff up here and over here and down here. It's saying get the forward direction of the NPC, multiply it by the update time, add that to the current position and write the new position. The difference here is this multiply. We're taking one of these values is the distance that the center raycast is seeing a hit at. There it is. It's this one here. This. I wish these cards would stay where I put them, but they keep moving. This bottom input to the remap here, that is the distance that the center raycast is seeing a hit at. So, 3.5 meters away, if I put something in front of the NPC, it gets a collision closer. And it's saying this 2 is the distance from the hit at which we start slowing down. This 1, which is also a value field, is the distance from the hit at which we are completely stopped. We remap this 2 to 1 range into a 0 to 1 range to get a multiplier for how slow we should go. And then we plug that into the existing logic here. So since this has nothing close to it, it's going to go at full speed. But if there's something in front of it, that's close enough that it stopped entirely. If it's a little further away, come on, somewhere in between there. There we go. In between the two distances, it will go at a slower speed, but not entirely stop. And that's all it's saying. I don't know. I'm guessing that just quick review of the logics didn't make a lot of sense by itself. But when you put it all together, you've got the things that say, if I'm walking along and get close to something, I slow down and then I stop. If I'm walking along and the raycasts show it's clear, we turn towards the target. If I'm walking along and the raycasts say that I'm about to run into something, then we start turning towards whichever left or right side has more free space available. And that gives you some very basic collision avoidance. Now, the biggest problem here is that if the NPC approaches an inside angle straight on, it can get stuck in the corner. I'll see if I can actively do it here. I'm trying to get him to walk into this corner here. Come on. Not that way. Where are you going? I suspect I'll just tell the NPC to walk to target. He's headed for it, but there happens to be a wall in the way. Uh-oh. Bad demonstration. He seems to have gotten stuck. This did not happen during my testing. Of course, it happened on video. Huh. So, yeah. It needs a little work still, but I'm happy with the progress so far.